In this video, I'm going to show you how to graph the absolute value of linear functions. Now remember, a function is an equation that involves both a y and an x. So the basic absolute value function is y is equal to the absolute value of x. Now to do this, we're going to go with our very basic first method of graphing, which is we're going to create a table of values for x and y, and let's choose negative and positive x values, and then we're going to substitute it into the function. So I'm going to go from -2, -1, 0, 1, and 2. So when I substitute -2 into x, remember now I have the absolute value of -2, which then becomes +2. And the absolute value of -1 will become 1, 0 is 0, absolute value of 1 is 1, and the absolute value of 2 is 2. So you can see that if I keep going, 3 will be 3, 4 will be 4, absolute of -3 will be +3, -4 will be +4. So let's plot our points on our grid here. And I'm going to assume that, let's say we kept going with our table. So we have all of these points here, and I'm going to connect them all. So make sure you use a ruler. So we can draw a nice straight line. And you can see that we get a nice looking V shape. Now this V shape, maybe it might remind you of the parabola. It does have a vertex, and in this case the basic absolute value function has a vertex of 0, 0. And notice the domain, we can keep going in the negative and the positive x direction. So x is all real numbers. And then the range, the smallest y value is 0, but it does keep pointing up. So we can say that the range is y is greater or equal to 0. Now, the absolute value function can be defined as two lines. So if you take a look, we can see a left line and a right line, a negative line and a positive sloped line. And we can define these over two different intervals. So when a function can be defined by two different rules for each interval in the domain, we call this a piecewise function. So a piecewise function is a function, and it's composed of two or more separate functions or pieces, each with its own specific domain that combine to define the overall function. So later on in calculus, actually, you will take a look at pieces that are multiple pieces put together to create a bigger function. All right, so the absolute value function can be defined as this piecewise function. So we can say that f of x, or you can use y as well, and I'm going to use my curly brackets. So we can say that the left side, this side over here, has a slope of -1 and a y-intercept of 0. So we can say that line is -x. And it is -x if x is less than or equal to 0. The slope, or the line on the right side has a slope of +1, and it also goes through a y-intercept of 0. So that equation of the right line is just x, and that occurs if x is greater than 0. Now we only have to define 0 in one of the pieces, so I've chosen to put the equal sign or the equal line when x is less than or equal to 0. But you can also write it with x is less than 0 and then put the equal sign for the second piece so that x is greater or equal to 0. All right, so from this graph we can see how y equals absolute value of x is related actually to the graph of just simply y equals x. Let's pretend that there was no absolute value. So if there wasn't an absolute value, we would actually get a straight line that goes like this. Okay. Now, since when we take the absolute value of a number, absolute value of x, and since that cannot be negative, we can see that the part of the graph that is below the x-axis, so this piece right here, is actually reflected over or in the y-axis. Okay, so you can see that here, -8 has now become +8. -7 now moves to +7. -6 is +6, and so forth. So we see that what is below the x-axis is then reflected in the x-axis. So it is reflected above. And then the part of the graph of y equals f of x, notice that this part that's already above, this part here, which I'll highlight in pink, this part here, it is already above the x-axis and is already positive, so that part actually remains unchanged. Or we can say that it stays the same. All right, let's take a look at an example. So we are given y equals the absolute value of 2x minus 5. All right, so the first thing I do want you to do is let's find the x-intercept and the y-intercept. So the y-intercept, we are going to plug in 0 for x. So here we get y equals, so 2 times 0 is 0, and we just have absolute of -5, which is going to be +5. So our y-intercept is 0, 5. And then we're going to plug in 0 for y. And for this one right now, we're going to ignore the absolute value symbol. Later on, I'm actually going to show you how to solve for x properly. But in this case, we can just ignore it for now. We're going to move the 5 to the right side. So 5 equals 2x. Divide both sides by 2. And x equals 5 over 2. So our x-intercept is 5 over 2 and 0. All right. Now we're going to take this and let's take a look at two methods of graphing. So the method that I've already showed you is to use a table of values. So I'm going to show you that again, and we have x and y. Let me write down the function again. So we have absolute value of 2x minus 5. So let's plug in, we're going to start off with our x-intercept. Remember that our x-intercept was 5 over 2, 0. So that actually is where our starting point will be. And we're going to place that in the middle of our table. 5 over 2, which actually, let's use 2.5. That makes it a little bit nicer. And that gives us a y value of 0. And then let's choose two numbers on either side. So we're just going to decrease systematically. We'll just go 2 and then 1. And then going increasing direction, we're going to go 3 and 4. So when we plug in 1, we get 2 times 1 minus 5, which is -3. And then the absolute value of -3 is +3. Do the same thing with 2. 2 times 2 is 4. Minus 5 is -1. Absolute value will be +1. And then 3. 2 times 3 is 6. 6 minus 5 is 1. And then last number 4. 2 times 4 is 8. Minus 5 is 3. Absolute value of 3 is 3. So we have 2.5, which we're going to plot right here in the middle. And then 2 is 1. 1 we get 3. Oh, sorry. Put that in the wrong spot. So 2 is actually 1 over here. 1 is 3. 3 we get 1. 4 we get 3. So it's actually a very skinny graph. So I'm going to connect, we're going to connect our points and we get something that looks like this. Now, one thing that you can use as your guide is we know that from here, the line is actually 2x minus 5. So we can think of the slope as being 2. So we can plot points right here and over here, knowing that the slope is 2. All right, let me show you the second method, which I actually like a little better because it's actually a little bit quicker. So let's graph y equals 2x minus 5. Let's ignore the absolute value symbol. So we have a y-intercept of -5 and we have the slope of 2. So I'm going to graph a whole bunch of points all along a line. I'm going to connect these points, and let's connect it with a ruler, but we're going to use a dashed line for now. Now, remember I said that anything that is above the x-axis, that remains unchanged. So this part here, starting at the x-axis, we're going to actually draw a solid line through here. Okay. And then anything that is below the x-axis gets flipped over to be above the x-axis. So here we have -5. That's now going to become +5. This is -3, becomes +3, and so on. Now the point here is 2/5, like we knew from before because we calculated the x-intercept. So we can connect this with our other points. So we get something that looks like this. And now we actually get the same graph. Now this bottom part, I'm going to highlight this. This bottom part here actually would not be part of the absolute value graph, but it's actually just the part on this top part here that is our graph. So I'll highlight that in blue. So it's just this will be our graph in the end. All right, now using our graph, let's state the domain and range. So the domain is all real numbers. And the range, we can see it's greater than or equal to 0, since that is our smallest value. And let's do this new part here. Let's express this as a piecewise function. Now, one way we can do this is actually, we'll start off with the function that we already have, which is 2x minus 5. So I'm going to write that first. And this occurs if x is greater or equal to 5/2, which is this point here that defines the right side and the left side of the absolute value. And then the left line is actually the negative of this 2x minus 5 function. So I'm going to put this as negative, and then in brackets 2x minus 5. And this occurs when x is less than 5/2, which is this x-intercept here. All right, finally, the last thing I want to talk about is something called invariant points. And that is a point that remains unchanged when a transformation is applied to it. Transformation here is our absolute value. So looking at method 2, we can see that the x-intercept of the original function is the same as the x-intercept of the new function, right? So we had our line, and then we have the v. So that is unchanged. So what are the points in the graph for invariant points? So if you take a look at the graph, all the points that were positive already right here are also invariant points. So we can say that all x's greater or equal to 5/2.